Okay, hello everyone. I'm Mr. McBride. This is SCH4U, balancing redox reactions 1 using oxidation numbers. Okay, so no great surprise, the Ontario curriculum specifies that we will be able to balance chemical equations using oxidation number method. Now we all know some of the assets of having balanced reactions. We've seen that using a balanced reaction we can calculate the amounts of reagents we need, we can determine the expected products of reactions, examine the energetics of a given reaction, and do more. And so we need to be able to balance redox reactions. The problem is there's a little bit more to balancing these reactions than the other ones we've seen before. And the reason for this is we need to be able to balance electrical charge. So there are a couple of potential approaches. We're going to examine oxidation numbers today and leave half-cell reactions for another time. Now, the exact way of using oxidation numbers depends on, for starters, whether the reaction is done in water, and then, if it is, whether it's acidic solution or basic. And so we're going to deal with both situations today. Alright, so step by step then, the oxidation number method. The first few steps apply whether it's in gas phase or in aqueous phase. First off, we have to assign the oxidation numbers to all the atoms in the reaction. And this is why we spent so much time talking about that yesterday. Once we do this, we can figure out how many electrons are moving per atom, and then make sure that the number of electrons being generated is the same as the number being accepted. So we're going to do a kind of a cross-multiply step. Once we do that, we'll find the simplest whole numbers for the reactants and determine the coefficients for the products, balancing first the oxidized and reduced, and then the rest of the atoms involved in the reaction. And this will become more obvious in a few minutes. What we'll do is we'll balance oxygen using water, and then we'll balance hydrogen by using protons. So these redox reactions that do occur in aqueous solution, it's very common for water to be involved in the reaction itself. And because of this, the pH will change as we go. We'll be able to see how the pH will change by following the oxygens and hydrogens in the reaction. And when we balance it, then to get an accurate representation of the reaction, we have to be conscious of whether it's an acid or basic solution. When we're working in acid, we're going to balance the reaction the same way as we do in gas phase, but then we're going to work with oxygens and hydrogens. This will become more obvious in a second. Okay, so let's take dichromate reacting with ethanol to form the carboxylic acid. So the first thing we want to do, the first step, is to assign the oxidation numbers for all of the atoms. Now there are some that we're not going to be sure about. Chromium is going to be a big question mark at first, but we've already seen how to solve this problem. Oxygen is almost always -2. Carbon, again, very versatile, right? But the hydrogen has a +1, the other oxygen, and again, a -2, and the other hydrogen a +1. Now this one's no mystery. Since there's a +3 charge, chromium has an oxidation number of +3. Carbon's another question mark, and again, +1 for hydrogen and -2 for oxygen. And when we're finished here, we can use our simple math skills in order to determine the oxidation numbers, just like we did yesterday. So if we follow the algebra through, the oxidation number for each chromium atom is +6. The oxidation number for the carbon, -2. And on the product side, the other carbon has an oxidation number of 0. And so now we have what we need to determine how the electrons move. So you can see that the oxidation number for chromium moves from +6 to +3. What this means is that the chromium is in fact accepting 3 electrons. Each atom's accepting 3 electrons. Carbon's going from -2 to 0. It's giving up 2 electrons. And we can immediately see that there's a bit of a problem here. Things aren't balancing out very well. So what we do to balance this is we involve the subscripts. And so we can see for each dichromate ion, we're going to get 3 electrons times 2, or 6 electrons. And for each of the organics with 2 carbons, it's going to give us it's going to give up 4 electrons. 2 times the 2 gives us 4. So now once we do that, it's trivial to see that we need to balance that out. And so we're going to insert multipliers to get an equal number of electrons. And I think if you follow this through pretty quickly, you'll see 2 dichromate ions times 2 chromium gives us 4, times the 3 electrons that it accepts gives us 12 electrons. Similarly, 6 carbon atoms, each giving up 2 electrons, gives us 12 electrons. So our electrons are balancing by inserting the 2 and the 3. And this is really done more by examination than anything else, and you can give it a quick check to make sure the electrons balance. Now, once we have this, we're going to see that the next step is to balance the oxygens in the reaction. So we can see 2 times 7, 14, plus 3 is 17 oxygens on the left, and only 3 times 2 or 6 on the right. So this means we're 11 oxygens off on the right, and we're going to need to balance this using water. So 11 water molecules will give us the 11 oxygens we need. Now once we're done that, we have to balance hydrogen. The good news is we can balance hydrogen simply by using protons. So if we do some quick math, we can see over here 3 times 5, 15 hydrogens. Oh, but wait, there's a hydroxyl group here. That gives us 18 hydrogens on the left. On the right, 3 times 4 is 12 hydrogens. But there's also 22 hydrogens over here. So we have 34 on the right and only 18 on the left. So we need to add, by my count, 16 more hydrogens on the left-hand side. And we do this by simply putting in protons. Now, because we're working in acidic conditions, this works out fine. There's lots of protons kicking around in solution to provide those to our reaction. But those of you with sharp eyes will realize that means the pH is going to drop as this reaction proceeds. Okay, so finally what we want to do is see if there's anything that's on both sides of the reaction that we could cancel. For example, some water or some protons or anything like this. We can also see if maybe there's a common factor across these, and of course there isn't because we have a 3 in it too. So there's nothing to do here. This is in fact our balanced equation, and if you examine it, you'll see that the charges all balance as well as all the atoms. So we have 16 plus here, minus 4 is 12 positive on the left-hand side, 12 positive on the right, and no charge on these. So the charge balances. We know the protons and oxygens balance because we just did that. Okay, so we've got ourselves a balanced equation. And of course we can check the carbons and chromium if we want to, but it should work out. Now when we work in base, there's just one extra step. Everything else is done the same way. So all we do is balance in the exact same manner, then add hydroxyl ions to both sides in order to balance the equation. Okay, so under basic conditions, let's take a nice easy one here. So we're seeing the oxidation state of nitrogen change when it's reacting with iodine. And this is an aqueous solution, and they'll always specify whether it's base. In this case, it is. Okay, so our first step is, as always, getting that oxidation state. So we know what the oxygens are. Iodine's in its elemental form on the left-hand side, so it gets a 0. And on the right-hand side, conveniently, it has that -1 charge, so we know its oxidation state. Now all we have to do is do the simple math to get the value for nitrogen. So on the left-hand side, it's a +3. On the right-hand side, a +5. So a quick examination, the oxidation number is going up. Nitrogen is what is being oxidized. And so we can be confident that iodine is being reduced. Okay, now how many electrons? Well, each nitrogen loses 2 electrons, and each iodine gains 1 electron. So we obviously need a multiplier in here. So we have to make sure that there are 2 iodine atoms for each nitrogen atom. So we put a 2 on the right-hand side, and that balances our electrons. So now what's next? Well, next we have to recognize that oxygen isn't balanced. There's 2 oxygens on the left and 3 on the right. So on the right-hand side, we've got to add a water molecule to balance that out on the left-hand side. We can see it there. And then next, we want to balance the hydrogens. Now in this case, there's no hydrogen on the right, so we're going to have to add 2 protons to the right-hand side to balance that. And a common mistake will stop there. Well, no, we have to realize that there aren't many protons at all in solution because it's basic conditions. So we have to change this up. So we simply add OH negative to the right-hand side to react with those protons to get rid of them and generate water. And just like in math class, anything we do to the right-hand side, we have to do to the left-hand side. So we add hydroxide to the other side as well. And we collect these guys together to form water. And then the last step, we have to cancel the water. You see how there's water on the left-hand side and on the right-hand side? Well, there's no reason for this. If we want to get a net reaction, we can cancel this water and eliminate the 2 off of the right-hand side. And with that, we have our equation. Now what we do is look for anything else we can cancel. In fact, there isn't anything else we can cancel. We can go ahead and check our charges. 2 times -1 plus -1 is -3. -1 plus -2 is -3. And everything else should cancel nicely. And in fact, it does. Okay, so to summarize, balancing redox equations is a bit more complicated than other reactions because we have to actually consider the electrons before we balance them. We have to sequentially first track the charge, then the hydrogens, then the oxygen as we work. And the precise approach we take depends on whether it's acidic or basic solution. But when we're finished, everything should balance. Atoms and charge should balance between each side. And so we can do a quick check and always make sure we get 100% on those questions. Okay, so for your homework, please read over the note again and finish up the balancing redox worksheet. Thanks very much and have a great night.